Okay, let's start this morning with an announcement. Well, a couple of announcements. The first one is that by today, NXP shall provide me the discount for letting you buying the boards. I will post an update on Portata Didattica. Most likely, they will give me vouchers. That is a code or a set of codes that you have to specify when buying the board through the buy direct system of NXP. So please have a look at the Portata Didattica in the coming days. I hope they are on time. So I hope to be able to post updates by tomorrow, I will say. Then in preparation of the practical lectures where we have to use Simulink, I will post instructions about what to install. Recently, MathWorks provided us with a platform support package for the board that you are going to use. This is a specific piece of software that allows you to program the board directly from Simulink. So all the operations that we have to do will be much quicker than what I was expecting due to the unavailability of that platform support package. The only option is that the only difference with what I already announced in my first lecture is that the platform support package supports only 2016A onward. So most likely it will be the case that we cannot use earlier version. I know that I told you to install 2014A, B, sorry. Somebody of you also asked me whether to install the newer version or the later or the older version. Before knowing that there was that support package available, I told to install 2014B. But I'm considering switching to 16A because it will make our activity much more efficient. So I think it is a good value for what we have. But anyway, you will see information on Portata Didattica as well. Last but not least, as announced, we will have practical sections using National Instruments tools. For this, you need to install a software package provided by National Instruments that is LabVIEW. I already have the file for installing this. It's a couple of gigabytes, so I cannot share this through Portata Didattica. Maybe after the Easter break, I will let a USB stick circulating with the archive of the file so that you can install directly with that. You can circulate the file among you so that you are ready when we have National Instruments lectures that will be the end of April. Okay. Okay, so now switch to this lecture. Today I am going to present you the last example on the ISO 26262 for this part of the course. Obviously, when we will go close to the exam, there will be other exercises, a kind of wrap-up exercises. This is the last one that I want to use today to close the chapter that we have seen so far about ISO 26262. So this is a sort of last exercise for this first part of the course. Starting from the lecture on Friday after Easter, we will start looking into more detail on some of the aspects of the ISO 26262. In particular, we will look into software testing to introduce the different methodologies that we are about to learn in this class. And then we will start looking into the model-based design. So we will start looking into how to specify software architectures using Simulink, how to generate code, how to integrate code into hardware platforms. This is something that will take some weeks before you become operative. So there will be time for procuring the boards, okay? So don't be scared if you don't have yet the board when we start the model-based design practical part. We will have to do quite a good amount of activities with simulation before we deploy things on real hardware, okay? So the example that I want to propose you has the same format that we have seen a couple of lectures ago. So I will introduce the item, then you will have time on your own to think about the different aspects of the concept phase of the ISO 26262. So you will have to analyze the item, defining the elements, defining the operational situations, defining the hazards. Then you have to do the hazard analysis and risk assessment, as we have learned, and eventually you have to define the safety goals, the functional safety concepts, and the safe state. This is nothing new. This is something that we already have seen together, but as I said, it is worth that you put this on your own at work. So what is eCall system? eCall system is a system that has been becoming deployed in Europe, in the US, or throughout the world in general. It is intended for providing an automatic assistant in case of an accident. So let's imagine that you are driving your car and then you run into some troubles and you hit a tree, as in this picture. Then today, if you don't have any specific support from your vehicle, you are on your own. So you have to be able to take the phone, make an emergency call to the emergency room or to the fireman or whatever that comes into your rescue. But if you are severely hurted due to the accident, you can do the call on your own. So the European Union, as well as other governments, decided to ask for car makers to integrate into their vehicles a kind of telematic box that is able to recognize that the vehicle underwent an incident and to issue automatically an emergency call. This is obviously based on an infrastructure where the vehicle is just one element of the infrastructure. So inside the vehicle, you have the system that automatically recognizes the crash. Then there is the GPS network to localize precisely the position of the vehicle. Then there is the 3G network to issue the call. Then there is an operational center that receives the call and alerts properly the rescue team, thus closing this loop. This is something going to be deployed in Europe. It is not yet mandatory because there has been a little delay on the deployment of the regulation. But anyway, this is something that will come in the few years on our new vehicles. And if you look to the tier ones, that is the companies involved in designing an electronic system to be deployed in vehicle, you can recognize that most of them are active on this. Just to give a few names, we can see Magneti Marelli, the telematics division is working actively on these kind of systems. Then you can have Vodafone Automotive, for example, that is the new brand of Cobra Automotive that is doing this kind of stuff. And there is Huawei that is entering the automotive market working on this kind of system. So this is something that stimulated a lot of interest because it is potentially a big market. You have to imagine that any new vehicle shall have this kind of item installed. So it's a million of units per year. So it is very interesting. So our job for today is to analyze the ISO 262, from the ISO 26262 point of view, this item. So the eCall is an electronic control unit responsible for detecting an incident, that is a crash or a rollover of the car. Then it is intended for sending the position of the vehicle to a service center that is notified that was an accident and that the car subject to the incident is in a specific position. Then we will not enter in detail, but if you look into the web, you can find more information about the protocol that is used in this communication. You can see there that besides the position and besides the notification of the incident, there are a lot of information that are provided. For example, the typical number of passengers that are on the car. This is something that you provide when you register to the eCall service. Then, in case of very advanced systems, you can have the actual information about how many people are in the car. You can have information about particular diseases of the people that are normally using this car. You can have information about some biometric data of this person, like, for example, the blood type and so on and so forth. So this is intended for bringing the emergency people with the most up-to-date and fresh information about the person involved in the incident, ready to operate on the incident site. For today, let's have let me say, a less detailed view of this. Let's think about how the incident is detected. We have to detect a crash or a rollover. This means that we have to exploit a number of sensors that are within the vehicle to recognize these situations. For example, the ECU will monitor the vehicle network to recognize for sudden deceleration. This could be an indication that in very few seconds we switch from 70 kilometers per hour to 0. But this is clearly something that shall not happen, or at least this shall not happen if you don't hit the brake pedal. Then you can also monitor the activation of the airbag. Today's any new vehicle is full of airbag, so if the airbag deploy, it means that we had a crash. Then we could also have accelerometers, and we have accelerometers inside the vehicle, and this can be used for detecting some changing in the orientation of the vehicle. This is important for detecting the rollover, for example. Then we have a GPS receiver. It could be GPS, it could be GLONASS, it could be Galileo, it depends. No matter what, we have an antenna attached with a receiver that is able to get localization information. And then we have, for sure, a modem, 3G modem, that is able to issue the emergency call. If you look into the architecture of this system, we can recognize these elements. For sure, we will have a microcontroller that is running software, that is the routine intended for interfacing with the different sensors and to recognize the crash and to issue the call. Then we have an interface with the vehicle through the vehicle CAN network, through which we assume for today that we receive the vehicle speed and the airbag activation flag. These are provided by another item that is the body computer. We will see this more in detail when we will look into the architecture of a vehicle, but this is something that we already mentioned multiple times. Within the vehicle, you have a network, a local area network, based on a specific protocol, that is the CAN protocol, through which the different ECU exchanges information. One of these is the body computer that provides, in our exercise, the vehicle speed and the airbag activation flag. So the microcontroller receives this input through the network. Then we have the GPS, that is the device to to fix the position. This could be simple, as in this case, or it could be more advanced, like we can fuse together the information we can get from 3G modem and the information we got from the GPS, so to have a better localization. For the moment, we don't care. We just say the fix, so the position is given by the GPS. Then most likely we have accelerometers. These are needed for detecting the orientation of the vehicle. And we have the 3G modem for issue the call. So this is, roughly speaking, the architecture of our item. What we have to do here, we have to analyze this item from the ISO 26262 point of view. We have to do the concept phase. So what I'm expecting from you is the analysis of the item, the identification of the operational situations that are relevant for this item, the analysis of the hazard, the identification of the ASIL, if applicable, for this item, and then I'm expecting functional safety concept, functional goals, functional safety concept, and safe state. Okay? As we did for the QA example, you will have time for working on your own starting from now. Then, after discussion, we will see my solution of this exercise on Portata Didattica. I will show you my solution of this exercise that will be downloaded on Portata Didattica. On Portata Didattica, I just uploaded the solution of the QA. Okay, so sorry, I forgot to do this in the past days. It is up now, so if you have the laptop with you or some sort of connectivity, you can go there to see that example as reference. Okay? So let's stop the recording now. We will walk for, I think, half an hour or 40 minutes, and then we will discuss the solution together. Okay. So sorry if I interrupt your reasoning about the exercise, but moving around the tables, I've seen that there are some doubts about what a microcontroller is with respect to a microprocessor. So I tried to put together these few slides so that I can give you an overview so that we have a set of common terms and so next time we discuss, we don't have doubts or misinterpretations. These are a few slides, so I will not steal too much time to the exercise, but I think it is good to have an understanding of this concept. Sorry if I haven't done this before. So what I'm going to show you here, first the reference architecture, and then how the different processor families can be used for implement this reference architecture. So we have to deal with an electronic control unit, ECU. So this is something that will deploy in our vehicle that is able to interface with sensor actuators and run software. Okay, this is what we have. Some of the sensors can be embedded within the electronic control units. Some others are deployed in the vehicle and sends data through proper communication channel to the ECU. It depends on the architecture of the vehicle. For the moment, let's keep the things simple and let's have this reference architecture. So the electronic control unit is a container where we have, from the functional point of view, a central processing unit, also called a microprocessor, that is able to run software. Then we have some memory that is typically divided in boot flash, mass memory flash, and RAM memory. What's the purpose of this? Well, all of you remember that the microprocessor, in order to run a piece of software, needs instructions and data. The instruction tells what the software has to do, The data are the elements that are manipulated by the instructions, okay? So this shall be stored somewhere. The instruction and the data shall be stored somewhere. The CPU is not suitable for storing all the instructions and all the data the software has to deal with. So we need other functionalities devoted to store instructions and data besides the functional unit, the microprocessor, the CPU, that is able to run instructions on the stored data. So the boot flash and the mass memory flash are basically the memories intended for storing the instructions, okay? So they are non-volatile memories. They are used to place the program our microprocessor has to run. Then, besides the microprocessor and the memory for storing instructions, we have the memory for storing data, and this is the RAM memory. The technology is different. The RAM memory is a volatile memory that is able to provide very efficiently data to the CPU when the instructions require those data. Obviously, we will have instructions to place data here, instruction to fetch data from here to make some manipulation, and other instructions to send back data inside the RAM memory, okay? Then, our processor is now able to run software, but it has to do something useful for us. So it has to be able to interface with sensors, with other items in order to get the data that we need for working, so the information provided by the sensor needed for working, as well as to provide the results of the computation to other items or to actuate some controls. Think about the electric motor that is used for bringing upside or downside the windows of your car. So there is a button that you press. This button gives an input to a microcontroller that as an output decides whether to rotate the motor in one direction or the other one to lift up or down the window, okay? So the I/O block, the functional I/O block that we see here is intended for this purpose. This is the input-output functional block. This is the channel through which the microprocessor is able to communicate with the rest of the world. Then, this could be set of, for example, ADC converter, PWM, communication network like CAN, Ethernet, serial line, whatever. This is where the communication takes place. Then, in our ECU, we can have sensors that are, again, considered as input elements, because these are the elements that could provide data to the CPU, okay? We could have also actuators inside our ECU. These are output elements integrated within the ECU container, but from the functional point of view, we can describe them under this block that is I/O, okay? Again, these are not discrete components. These are functional units. Then the functional units can be mapped into multiple components or could be integrated all inside the same component. It depends on the processor family that we will use for deploying this reference architecture. So again, the boxes that you can see here are not to be confused with microchips. These are not intended to be microchips in this picture. They are functional units. They are units able to execute instructions. They are units able to store data. They are units able to store instructions. Then, in one implementation of this reference architecture, they can be integrated into a single chip. In another implementation, they can be spread among multiple chips, okay? Then, all the things are interconnected. Indeed, the microprocessor is able to talk with RAM, I/O, mass memory, boot flash through a suitable set of buses. That is a set of wires that exits from the CPU and enters in the other devices and in the other functional units and vice versa, okay? Then, if you go back to your memory of computer programming or informatics or whatever was the name of the course when you started Politecnico, these buses are divided in address, control, and data, okay? Don't care for the moment, we can move forward without going into more detail. Then, now that we have seen the functional units, let's look into the hardware that could implement those functional units. So let's look into the processor families that are the set of physical components that we can use to put together the reference architecture that we just discussed. In this case, if we look into the market, we can recognize a number of different families that can be somewhat defined by taking into consideration cost on one axis and performance on the other. So cost is the number of dollars that you have to pay for buying one item of that specific processor family. The performance is a measure of how fast or capable the processor family is to execute software. In order to get a measure that everybody understands, even if it is not always the best way for expressing the performance of a processor, we consider the clock frequency. So how fast we can clock our device with an oscillator. So as you can see in this chart, on the bottom end of this picture, we have the microcontrollers families. We will see in a minute what's the meaning of microcontroller and also the others. So let's say that for the moment, without knowing which is the physiognomy of a microcontroller, let's just consider this very rough analysis. It is something that costs from $1 to $20 for each component, and it is working at a speed from 50 megahertz to 120 megahertz, more or less. So it is something cheap and slow. Then we have a number of other possibilities that are the microprocessors that, again, without knowing the details, it is something that could cost from $10 up to $500 for a single device, with performance ranges from few hundreds of megahertz well into the gigahertz range, okay? A subclass of the microprocessor is the digital signal processor that is a specialized family intended for number crunching operations. So if you have to process the data coming from a radar that has to do a lot of computing in order to filter the data, recognize features, and do whatever you can imagine, then you may want to have something specialized for that task. And this is the digital signal processor. Again, this is something in the range from 100 to 1 point something gigahertz, and the cost is again from few tens of dollars up to some hundreds of dollars. Then we have a broader category that embraces all of them that I call the hybrid. This is because inside a single family you have elements of all the others. We can see this later on, okay? So far we have considered just a very broad overview of our families, just considering cost and performance. Now let's delve into them and let's have a better understanding of what we can find here. So the microcontrollers embeds the RAM, the flash, the peripherals, the real-time clock, and obviously the CPU. So all the functional elements that we have seen in the reference architecture are contained into a single chip. So very cost-effective, low performance, but everything is inside. This has some drawbacks, the sense that we could have an expandable memory. If the memory is integrated within the chip, you cannot open the chip to fit new memory inside, okay? But on the other hand, this is very helpful to build a system that is very simple. You don't need to add extra hardware. You just need to provide the power supply, and that's it. So if you have very low cost needs, this is a good solution. Think about automotive. In automotive, you have volumes of some 100,000 samples or even millions of samples. So what you want to do is to save as much as possible. You save 1 cent in 10 million production can be a big figure, okay, in cost saving. So you want to have something like microcontrollers, and you want to try to extract as much as you can from the few megahertz that you have there. This is because everything is integrated. Making the system is simple. The microprocessor, you have the CPU within one chip, and maybe a few other elements like, for example, the I/O interfaces. So if you think about the reference architecture, we draw a line around the CPU and I/O, and they are the content of the microprocessor. This is not enough for operating. You need a place to store the instruction, you need to have a place for store the data. And these are additional components that you have to place besides the microprocessor, okay? The digital signal processor is exactly as the microprocessor, but the internal features of the CPU are designed to execute some specific class of applications. Last but not least, we have the hybrid. The hybrid is something that is based, as I said, on combining together elements out of the other families. So we could have microprocessor plus microcontroller, microprocessor plus microcontroller plus DSP, microprocessor plus FPGAs, microprocessor plus GPU. So besides the other families, the hybrid is now extending also to some specialized hardware like field programmable gate arrays, so that you can implement your custom hardware inside the same chip that hosts the microprocessor. Or you can have the microprocessor that integrates also the graphical processing unit. So if you have to implement a system that has to do some image processing, well, and image display, you can do this with a single device. So just to give you some more details, here I try to categorize the different instruction sets, that is the different internal architecture of the CPU in terms of instruction set architecture, so in terms of the different solutions that are available in the market, and the market for which this instruction set applies. So nowadays ARM is, let me say, getting all the market share. Most likely this will happen in few years. If you look into your smartphones, you have a microprocessor. Probably it is an hybrid where you have the microprocessor plus the GPU plus some IOs, and it is 99% of the cases based on ARM instruction set architecture. This is also used in industrial and in automotive, and the presence of ARM in automotive is growing. AVR is another instruction set. How many of you does have an Arduino 1? An Arduino 2? Okay. Well, that is based on Atmel AVR architecture. If you look into a lot of very budget applications like the alarm system that we have on the ceiling for detecting smoke, it is very likely that it is based on a cheap AVR device. If you look into the microcontrollers that are controlling small electric motors in your vehicle, it is very likely that you have an AVR there. Then Intel x86 is in commercial, industrial, mill, and aerospace. Besides whichever laptop or computer you could have that is based on Intel x86, you can find the same components also in a number of other applications. If you have to control an industrial robot or an industrial production line, it's very likely that you need a lot of computing power. And this is provided by Intel machines. If you are looking into equipments that are shipped on military ships, for example, or on board heavy-duty vehicle for military use, especially in the communication apparatus, you have plenty of examples of Intel 86 architectures. Then MIPS is something that was pretty famous a few years ago. Nowadays it is somewhat disappearing. This is today mostly used within consumer devices like printers. If you have an inkjet printer or a laser printer, it is likely that the processor that is inside there is a MIPS. PowerPC is an architecture that has been on the market since 20 years, more or less, even more than that. I think it is 30 to be more precise. This is widely used in a range of applications like automotive, industrial, mill and aerospace, telecom. So today, most of the engine control units are based on PowerPC architectures. Spark is something similar to MIPS. It is something that was popular a few years ago, but today it is more or less disappearing and is confined in very specific applications like consumer for the printers, let's say, and military and aerospace, especially aerospace. In Europe, the European Space Agency spent some hundreds of millions of euros in the past 15 years to develop a line of microprocessor for space use based on this instruction set architecture. Then let me give you a few other details just to better, let me say, represent the scenario that you can find when deploying the different processor families. So let's imagine that you want to build an electronic control unit using a microcontroller. It is very likely that you need few stuffs like the microcontrol unit that contains all the elements that you need, the memory, the I/O, the CPU. Then you have to bring a reference oscillator and a power supply, and that's it. If you look at pictures on the web of an electronic control unit, it is very likely that you will see a big device like that is the microcontroller, some other devices that are the voltage regulators, and then you see a lot of discrete components, capacitors, resistors, diodes, stuff like that. But these are passive components. If you look at an electronic control unit, the active component is just the microcontroller plus the power supply stages. This is because with this approach we can save a lot of money. Example of microcontrollers, for example STM32F7. This is the newest in the offer of STM. You can see that besides the processor, the blue box here, ARM Cortex-M7 CPU 200 MHz, we have a number of other elements like the memory, 1 megabyte of flash, 320 kilobytes of RAM. We have specific IOs intended for control, like PWM, timers. We have analog interfaces like DAC, ADC, temperature sensor. We could have specific features for some specific tasks like encryption. And then we have devices that are intended for keeping the system up and running. So with this single device, you can build your ECU. Other example, the Kinetis K70. This is the one that you have on the Freedom K64. You have the computing core plus memory, clock, interfaces. So again, you have inside a single chip all the functional elements that we have seen in our reference architecture. Then, if we move to the microprocessor DSP, you can recognize that the system is becoming more complex. Besides the component integrating the CPU, that is a general purpose CPU in the case of the microprocessor, or a specialized CPU in the case of the DSP, we have memory, the power supply, the oscillator, and then we could have a dedicated interface between the microprocessor and the memory. This is needed or not, depending on the features of the red square that we have here. If the component is able to host the memory bridge, well, this orange element shall be considered as integrated into the red box. If not, this is an additional component that we have to place besides the CPU. This is important to consider because you have to remember that the cost of your system is not just given by the bill of materials. So when you have to consider the cost of an ECU, you don't have to just look at the list of components, make the sum of the prices, and that is the total cost. So the bill of materials is just the list of components that you have. When you build a system, you need to design a PCB. So more components means more layers inside your PCB. So it is an additional cost. If you have to manufacture a 3 layers board, you can do for 20 euros if the board is not too big, and you can print boards through online services. If you have to do a 20 layers PCB, it's a totally different story. The cost doesn't scale linearly, it's geometric, okay? Then you have to consider the mounting process. If you have to assemble a board with 6 components, let's say with 100 components, or a board with 300 components, it's a totally different story. The time for assembling the component is higher, obviously, because you have more components to manipulate. But then you have to test the hardware to check whether it is working, because you don't want to ship to your customer a faulty hardware. So the more components you have, the more you have to test. And so the higher will be the cost. So the fact that you are using a microcontroller doesn't just make the PCB simpler and the bill of material shorter. It also gives you significant advantages on the production side and the production cost, okay? So this is something that you have to envision. So the fact that here we have more colored blocks besides the red one that contains the element that is able to run software makes a big difference. If you have to manufacture 1 million components, saving 30% of the cost is a huge saving, okay? These are examples of microprocessor like Intel. This is the i7, the one that is probably most of your computer. You can see that you have the computing cores, so the CPU, integrated on the same die with the memory controller, so we don't need the memory bridge to be placed outside the processor because it is already contained, plus other memory and some interfaces. Okay, now let me show you something about hybrids. We can see here that we have more or less the same PCB architecture, and then what we can find here? Well, it depends on the type of hybrid. For example, if we look into the high-end device from TI, we have 4 ARM A15 CPUs, besides 8 DSPs, plus a number of interfaces. So you can clearly imagine that this is not to be a cheap device, and this is not something that you have to deploy for very trivial tasks. So if you have a very computing-intensive applications, then you want to have such a kind of beast. Otherwise, it is an overkill. This is an example of Zinc device. You may have heard about this. This is an example of a single chip that hosts processor plus FPGA. And this is the last example, the NVIDIA Tegra K1. You can see here that we have computing cores besides the graphical processing unit. This is a device that is one of the contender of the radar for automotive application, because thanks to the capability of the graphical processing unit, it could perform a massive amount of computation in a very compact form factor with very low power consumption. And this is very appealing for automotive, for example. Other type of applications where you can find this device are set-top boxes, for example, or some types of smartphone and tablets that are all powered by this kind of devices. Okay, so here I gave you a very quick look to the hardware that you can find in your electronic control unit. So I hope that now the difference between microprocessor and microcontroller is clearer, so that you have a better understanding of the terms that we are using in this class. So it is 9:29, so what do you want to do? Do you want to still work on your own on the exercise, or do you want me to show the solution? What do you prefer to do? So you want to see the solution, okay. So you don't want to work, you are lazy. Thanks God we have a bit of vacation, so you will be refreshed and restored, and you will be able to start working more intensively. Just kidding. Okay, so let's see the solution of this. The first thing that we have to do is to do the item definition, okay? So the process is always the same. Let's define the perimeters. Let's look what we have to deal with, and then we proceed. So the item is composed of an electronic control unit for the eCall that is made of a microcontroller. So we have the CPU, the embedded memory, and the CAN interface, everything in a single component, according to what we just said. Then we have, as a separate component, integrated on the same electronic control unit, but most likely implemented by a different device than the microcontroller, we have the GPS. Then we have accelerometer and the 3G modem. So our item integrates all these elements. Which kind of interaction we have? We have interaction through the CAN network with the body computer to receive the vehicle speed and the airbag activation flag. Then we do not provide functionalities to other items. This is a self-standing item. Once the data that are sensed from the vehicle suggest that there is an issue, we make a call home saying, hello, please help me. We are not doing anything else, so we are not providing any other service to other items. This is not always the case. There are other examples where we need to get information for other items. Think about the ECU for braking. The ECU for braking contains a slope sensor that is used for assisting the start when you are on a slope. Well, this is an information that is distributed to other items. For example, to the powertrain, so to the electronic control unit for controlling the engine, that based on the slope in which the vehicle is moving can take different actions. Then we require functionality to the body computer to provide the vehicle speed and the airbag activation flag. Okay? This, I think, is pretty simple. Now, let's look at a more complex part of our investigation, that is the analysis of the hazards. So, this is something that I bet nobody of you would have done properly. So, the identification of the operational situation. The operational situation that we have to consider is the operational situation where the service provided by the item is relevant. So who cares about the item if we are driving safely? We care about the item if we are in an incident situation and we have life-threatening injuries. That is where the item can make the big difference. If it is working, it is likely that the item will save my life. If it is not, I will die. Okay? So the operational situation we consider is just one. The car is experiencing an incident with life-threatening injuries. This is our use case. This is our operational situation. Okay? If you don't think accurately on the function provided by the item, it is very likely that you end up with the typical operational situations that we have seen in the past lectures, driving at low speed, driving high speed in a congested road, and so on and so forth. Totally wrong. You have to consider the operational situation where the function provided by the item is relevant. We have an incident. If you consider the other driving scenarios, guess what you will get? The item is issuing a call when it is not needed. QM. Okay? Different story if you have an incident. If you have an incident and the item doesn't do the call, well, we are in troubles. Okay? So that's why this item is relevant, because it gives me the chance of showing you an example of operational situation that is not trivial at all. Then, what about hazard identification? Well, let's do a bit of failure mode effects analysis. So let's consider the different elements of the item. Let's consider a fault in each of them. Let's consider which is the outcome in terms of hazard resulting from that fault. So let's imagine that the GPS is not working. So the GPS is not able to fix the location. The item is not able to provide position information. This is our first hazard. Remember that the item should say to the emergency operator, the car is there, so send the ambulance there. If there is 30 kilometers away, well, that's a problem. Okay? So the lack of correct localization information is an hazard. Other device that could get broken is the accelerometer. So let's say that the accelerometer is not able to detect the rollover. This could happen. Accelerometers are based on microelectromechanical devices. They are very little mechanical parts that moves, and then by reading these movements, we can tell which is the projection of the gravity on the different axes on which the accelerometer is built. One of the failure modes is the stitching. So the mechanical blade that moves within the component could be stitched, so it could be unable to move anymore. This is one of the failure mechanisms that is available. This means that the accelerometer is not able to provide the functionality, is not able to tell that we have, for example, rollover, or we have a sudden change in the direction of speed of movement of the vehicle. The hazard here is the item is not able to recognize the rollover condition. Other element that could get broken is the microcontroller. So what if the microcontroller is not able to run software? Well, the item is not able to issue the emergency call. If we want to be more exhaustive, we could also say that the microcontroller, due to default, is subject to another hazard. That is, it issues the emergency call when it is not needed. Okay? But this is QM. We don't care. We do not have an accident. We do the call when it is not needed. It is QM. Then 3G modem, it is not able to make the phone call. So we are not able to tell anybody that we are in an emergency situation. The network could get broken. So we are not able to detect the change of the vehicle speed, neither the activation of the airbag. So we do not have inputs for, let me say, running our algorithm. Question: why we do not consider body computer? Why we do not consider a fault in the body computer? Right answer. We do not consider faults inside the body computer because it is outside the item. It is not part of the elements of the item. We have to consider only the elements of the item. Okay? Then, considering the operational situation and the different hazards, we have to rank them based on exposure, controllability, and severity. Okay? So, which is my solution? Here it is. In terms of severity, it is 3. We have said that our operational situation is we are in an incident with life-threatening injuries. So it is by definition 3. Okay? Then what about controllability? Controllability is 3. We do not have any controllability means here. We are not able to push a button to make the phone call. We are in an incident situation with life-threatening injuries, so we are possibly not able to move. Okay? So we cannot make any action to ask for the item to make the call. So the controllability is 3. But what is saving our life, and it is making the cost of this item not very high, is the fact that the exposure is low. Remember that exposure measures the probability of being in the operational situation for which the hazard could produce harm to people. So we can define this, for example, through the percentage of operational time. Think about the amount of time for which you use the car, and think about the amount of time you spent being in an incident situation with life-threatening injuries. In 25 years of driving, I never had this case. I think this is probably the same for all of you. If you look into the statistics, it is true that we have incident, but it is also true that the total amount of time of being in an incident with life-threatening injuries is very low. So exposure is 1, because it is very improbable that we are in an incident situation, okay? So thanks to this analysis, you can make the sum and you will see that it is 7. So this means easy lay. So we have to design for an easy lay. Even if we are in incident with life-threatening injuries, the probability of being in that situation is so low that the risk is easy lay. Remember that the risk is a combination of 3 elements: the exposure, the probability of being in the critical situation, the severity, how much bad is the result of the accident, and the controllability, how much you can take control of the vehicle that is not doing what you intended to do. Here, we are very low in terms of severity and, very high in terms of severity and controllability. We can get very badly hurted and we can't control. But luckily, exposure is low. The probability of being in an incident is low. So the result of the hazard analysis and risk assessment is just A. Okay? If you make the wrong decision here and you get confused by the fact that there is a life-threatening injuries, you can easily come to the ASIL-D conclusion. So you will spend a lot for designing your item, much more than what is reasonable to do, okay? So, what about the safety goals? Well, first of all, items shall be able to provide updated information about vehicle position. Driver shall be informed whether the item is not operating correctly. So, the driver could go to the workshop to have the item replaced, or could enforce some more safe driving style. The item shall be able to recognize incident occurrence, so it is not admissible that we run into an incident and the item does not make the call because it doesn't recognize that there is the incident. And then the item shall be able to issue the emergency call. Driver shall be informed whether the item is not operating correctly. Okay? Then how can we obtain these goals? Through functional safety concepts. These are possible implementations. The item shall combine GPS signal with localization based on cellular network. So if we are in a place where we have issues receiving the GPS signal, we are in an urban canyon, we are in a tunnel, we are in a place where GPS is not disseminated adequately, then we should find a way for knowing where we are. We can use the cellular network to exploit the triangulation process, and we can get the fix anyway. Then the item shall provide self-testing capability to identify failing components and shall be able to inform the vehicle user promptly. For what concerns the recognition of the incident, for example, we can have accelerometers with multiple axes to detect rollover condition and sudden deceleration of the vehicle. This can be done to compensate for the lack of data through the CAN network. So if we use an inertial platform, we are able to detect which is the position of the vehicle in space. And so even if the CAN network is not working, we can get information to recognize the incident. Other example, what can we do if we do not get the information about airbag deployment? Well, for example, we can think to have a microphone. Very simple pressure sensor with a threshold up to the sound of the exploding airbag. You may know that the airbag is deployed through the explosion of a little explosive charge. This is because due to the time in which the airbag shall inflate, only the gases produced by the explosion can be able to inflate the balloon fast enough to fulfill the requirement. So there is a big bang when the airbag deploys. This is something that you can hear through a microphone, and you can use this to recognize the deployment of the airbag, even if the CAN network is not saying you anything. Okay? Then, what about the other, well, the item shall be able to issue emergency call and drivers should be informed if it is not the case. We already said that we have testing capabilities. So we have the capability of recognizing that there is a failing component. Last but not least, the safe state. In case the self-test identify, oh, there is a typo here, failing components, the item must be disabled and the driver informed. So let me correct this. So the safe state is where the item is offline. So the item recognizes that it is not providing the intended service, so it stops working and says the driver go to the workshop to have the item serviced, typically replaced. Okay? So what's relevant here? Here, in this exercise, the operational situation is very relevant. You have an example of non-trivial operational situation. I remember when I gave this exercise at the exam, there was really a disaster out of the results of the students, because this is a not trivial example. Other element to be considered is the hazard analysis and risk assessment. You have to weight correctly exposure, severity, and controllability. And then, as you can see, also the functional safety concepts are not trivial at all. Think about the microphone. Okay? So, this is not to scare you, but anyway, it is important that you think adequately on the item, when it is needed, what the item is doing, and based on that you derive all the steps that are needed for the hazard analysis and risk assessment. Then the activity that you do when defining the functional safety concept shall take into consideration the ASIL. So if the ASIL is A, we have to spend little, because the risk is low. If the ASIL is D, you have to spend a lot, because the risk is too high. Okay? Any question? Yes, please.
How am I going to change the functional safety?
If there is what?
If the ASIL is different.
If the ASIL is different. So let's say the ASIL is D. If the ASIL is D, this means that you cannot lose the functionality. So it is not admissible for you to say, I'm not working, go to the repair shop. You have to provide some sort of functionality, either full functionality or degraded functionality. This can be done, for example, through a microprocessor that is able to work even if we have failures. This is done, for example, by redundancy in the network. This is done through redunding the GPS, redunding the modem, and so on and so forth. So if ASIL is D, you have to put more. If it is C, you have, let's say, close to D, so it is justified to put something. Maybe you can save on some item, on some elements of the item. If it is B or A, it's more a matter of process than of redundancy. Okay? Any other question? Well, we see this at the end of the teaching period when we will do some exam examples. Any other question? I have been told by some of you that the lecture of Friday is not yet online. I don't know if this is still the case, but well, I will check and I will let you know. And then that's it. Have a good Easter break, and we see again on Friday, April the 1st.